Over a week ago, we learned about a discovery that was made in 1819 by Hans Christian Ørsted. That discovery was, quite simply, that electricity generates magnetism. There were no conditions attached to that. If you had moving electric charges or an electric current, you would produce a magnetic field. Every single time, current produces magnetic field. Every single time. Now, yesterday we learned about a discovery made 12 years later in 1831 by two guys independently of one another, an American named Michael Faraday and a British guy named Joseph Henry. Might I get those mixed up? Anyways, Faraday and Henry, okay, one of them was British, one of them was American. Their discovery was essentially the opposite of what Ørsted's discovery was. They said, sure, electricity generates magnetism, but magnetism can generate electricity as well. But there's conditions associated with this one. It's if and only if a couple of conditions are met, or one condition is met. Okay, again, Ørsted, you have an electric current, you always generate a magnetic field. With Faraday and Henry, you got a magnetic field, you sometimes generate an electric current. You're going to generate an electric current if you do one of three things. What are those three things? What are those things that cause an electric current to be generated, given that you have a conductor and a magnetic field? What's one of them?
Move the wire.
Yeah, move the wire. If you move the wire relative to the magnetic field, then you're going to generate an electric current in the wire. What's another one? Kind of goes nicely with this one, right, Christian? Yeah, if you move the magnetic field, it doesn't matter which one you move, right? Here's a wire, here's a magnetic field. You move the wire this way, or you move the magnetic field this way, it's the exact same effect, right? It's relative motion. So if one moves, it's exactly the same effect as if the other one moves. What's the third one? It's kind of different than the first two. Yep. Yeah, change the strength or the magnitude of the magnetic field. Make it stronger, make it weaker. You're going to induce an electric current in the wire at that point. Does that make sense? So Ørsted, electricity generates magnetism always. Faraday/Henry, magnetism generates electricity sometimes. If you've got a wire and a magnetic field, one of them moves or the magnetic field changes in magnitude. All right, the demonstration that you just witnessed involved a concept called Lenz's law. We know from what we learned just a few minutes ago, what we learned yesterday, we know that Faraday and Henry said that when you have a conductor, and this copper tube is a conductor, right? And you have a magnet, and you move one of them, then you generate a current. That's what happens. When everybody else, okay, when Zach dropped the piece of steel, this didn't happen. But when everybody else dropped the magnet was moving relative to the conductor. That generated a current in the conductor. There was a current produced in the copper tube. We're going to say that B1, magnetic field number 1, that's the magnet that everybody else except Zach dropped, generates a current, I. Okay, B1 generates I. But there's a current now, and that current, albeit a very weak current, will generate a magnetic field. That's what Ørsted taught us in 1819. So you've got a magnetic field that's generating a current, and now you've got a current that's generating a magnetic field. B1 generates I, and I generates B2. Now you get two magnetic fields. These two magnetic fields will always act together. Whenever we have two magnetic fields, there's an interaction, right? These two magnetic fields will always act together. And this is the crux of what Lenz said, because everything else had already been said, right? Faraday said that magnetic field moving through a conductor generates a current. Ørsted said that a current generates a magnetic field. That stuff was already said. This is what's new. These two magnetic fields, the one that we started with, the one that we dropped, and the one that we just generated from the electric current, those two magnetic fields will act together to oppose the motion. They have to oppose the motion. They need to oppose the motion. You know there's going to be a force. There's two magnetic fields. You know there's going to be a force. And it can't be a force that helps the motion, because then the thing would speed up at a rate greater than 9.81, right? I dropped a magnet. It accelerated at a rate of maybe 3 meters per second squared. If I dropped a magnet and the motion wasn't opposed, If it was helped along, then it would accelerate at a rate of, let's say, 12 meters per second squared. That would violate the law of conservation of energy, because you'd end up getting more kinetic energy at the bottom than you had potential energy at the top. And that can't happen. So if there's going to be a force between the two magnetic fields, the one that I started with and the one that was generated by the electric current, B1 and B2, it must be in a force that opposes the motion so as to not violate the law of conservation of energy. Got it? Zach? The current's in this copper tube, so it would go around the copper tube.
Oh, it goes like in a circle.
Yeah. Now, I mean, it's so ridiculously small that I'm never going to feel that, right?
Yeah.
Not only did I not have to worry about my safety when I was holding onto that, I didn't even have to worry about feeling it or getting any kind of shock because it's so small. But it's there. It's there, weak because, well, you were dropping, it wasn't moving very fast, right? I'm going to draw a coil of wire here. Notice what's conspicuously absent from this coil of wire is some kind of core. You see what's happening in this coil? You see the wire in the front, the wire in the back. The wire in the back is the dotted line, the wire in the front is the solid line. I'm going to put a light bulb here. This is a symbol for a light bulb. You don't really need to know that, but just some kind of load. Maybe it's a light bulb, maybe it's a doorbell, maybe it's a motor, whatever it is. Okay, something that can be powered by electricity. Notice there's no current going through here yet. So this light bulb is turned off right now, right? Zero current going through here. Let's put a magnet right here with a south pole and a north pole right here, and let's move it to the right. Now what do I have? I've got a conductor, which is this coil of wire, and I've got a magnetic field, and I'm moving one of them. What happens? When I've got a conductor and a magnetic field, and I move one of them, doesn't matter which one, I generate a current. I generate a current in this wire. Which way? Don't know. That's what I'm going to find, actually. But that current will generate a magnetic field, a second magnetic field. This is B1. This is magnetic field number 1. There's going to be a second magnetic field, B2, generated by the current. That second magnetic field has to act together with the first one to oppose the motion. So in other words, the polarity of this coil becomes north on the left side, south on the right side. Imagine if it was the other way around. If it was south and north, that wouldn't oppose the motion of this magnet. That would help the motion of the magnet, right? It would pull it through. That make sense? It has to push it away to oppose the motion. That means if the polarity of this coil is north on the left side, south on the right side, the magnetic field inside goes to the left from south to north. We can use our little coil that we made with a piece of paper. Fingers are actually the current thumb field. Thumb goes from south to north. Fingers are going to go down in the front, up in the back. That means the electric current that's induced here is going to go clockwise. So we just determined the direction of the electric current here by knowing Lenz's law, by knowing that the force has to be a repulsive force, and therefore determining the polarity of this coil. Let's do another one here that looks almost the same. Here's our coil. Here's our light bulb. We're going to draw a magnet again with a south pole and a north pole. We're going to draw it again going to the right, but this time it's on the right side of this coil rather than the left side. We got a magnet. We got a conductor. When we move the magnet, what happens? You get a current produced in the conductor. Which way? Don't know. But we know that that current generates a second magnetic field that we call B2. The red magnetic field, the red one over here was B2. We got a red magnetic field generated over here that's B2 as well. What's the polarity of that one? Well, this time we've got to have a north pole on this side and a south pole on this side. Didn't we say it has to repel? No. We said it has to oppose the motion. If I want to oppose the motion of this guy over here going to the right, I have to repel it. If I want to oppose the motion of this guy over here going to the right, I have to pull it back, attract it back. Make sense? That's why I need a north pole right there to attract it. That's why I need a north pole right here to repel it. So if this is south and north like this, we take our little wrapped up paper coil again. This time we're going to stick our thumb towards the right. Fingers are going to go up in the front or down in the back. The electric current is going this way, up in the front, down in the back, around like this. So we would say the the current in this case would be clockwise. Counterclockwise in the first case, clockwise in the second case.